Greetings everyone and welcome back to the Greetings everyone and welcome back to the JohnAudioTech channel. We have some more fun in store for you. Yeah, I am progressing on the audio amplifier project. I need to get the output stage on a board so I can run it at full power, so I can play around with the voltage amplification stage and start to put it all together from there. But in the meantime, I want to play around with testing the stability of some amplifiers. So what I'm going to do is take the Field-Tech and hook it up to the input of amplifiers and put a load on their outputs and connect some capacitance across the output and see how stable the amplifier is. Now I have this color changing LED. What it is just a microcontroller that's driving this color changing LED. Well, I mean it's an RGB LED and it has 3 outputs. One for red, green, and blue. But anyhow, what I want to see is the square wave function of this chip, see how well it works versus the Field-Tech. So what I've done is I've taken a couple 100 ohm resistors and made a 50 ohm termination here to connect to it, because the source impedance inside is 50 ohms, and I want to see how that looks on the scope with the proper termination. Now I used to have a coaxial cable I could plug directly into the scope. I had a little T and I could put a 50 ohm terminator on there, but as luck would have it, I got rid of it a long time ago, so I don't have that option. So I'll just have to test it this way. Okay, so what I'll do here is put the scope probe directly across the output, and I'll point the camera at the oscilloscope, and we'll take a look at the performance. Okay, we're looking at the waveform. Of course, with the 50 ohm load, the output is greatly reduced. We're at 100 nanoseconds there, and you can see there is a little bit of wiggling going on there at the top, a little bit of ring, and it's just rounded at the bottom. You can see the slew rate there. We're looking at both the rise and falling edge at the same time. That's why you're seeing it that way. So, that's about as good as it's going to be. If I take off the 50 ohm resistor and then put the leads direct, of course I have to turn it down. You can see there a little bit of a peak going on, a little bit of ringing. It's about as good as I'm going to get here. So what I'll do next is take this microcontroller here and reprogram it to give me a 10 kilohertz square wave output. I just want to see if the output of this is any better than the Field-Tech. So be right back with that. Okay, I got the little micro programmed with 10 kilohertz, 50% duty cycle on the output here, and I'll just probe across its output there. That's giving us the signal. I do have a 470 ohm resistor across its output. This cannot really handle a 50 ohm load because its output's limited to 25 milliamps. So with this, it'll be 10 milliamps or so. And that's fine. It doesn't really matter because the input of our amplifier is going to be very high impedance anyway. So at this load, having a little slightly additional load won't affect it much. So let's take a look at the oscilloscope and see how this performs. Well, look at that. That's actually better than the Field-Tech. I might just have to use the microcontroller as a square wave source. I think the slew rates may be a bit faster. I'd have to go back and look at the other one and see and compare. but there's no ringing. You can crank it up. Yeah, I think it does slew a little faster. See if I can get my finger off that. There's a slight bit of ringing, I guess. Let's crank that up higher and look at it. Oh, I always grabbed the wrong knob. Good enough. So we're back at 100 nanoseconds that we were with the Fieldtech. The amplitude, of course, is going to be lower on the microcontroller because it's only designed to handle 5 volts max. We have 4.5 volts with the batteries there. 1, 2, 3, 4. Yeah, it's about 4 volts of output right now. So yeah, I'll just use this. Okay, so now I connected a potentiometer. So now I can vary the signal because I don't want to put the full 5 volts or whatever into the amplifier. You can turn it down to a more desirable level. Here is the signal. We turn it way down. That's at 10 kilohertz. If I turn that double edge thing off, you can just see it as a normal square wave. I have to check my scope probe. I checked it. It has a little function here on the scope. You can check and adjust the little capacitor, the trimmer capacitor on the scope probe, but you're getting a little bit of a peak. So it could be from the probe leads. Okay, I got the microcontroller connected to the input of the LM1875 lab amp. This is one of those kits you can buy off of eBay. And using a 4 ohm non-inductive load, scoping across the load. Let's see what kind of output we get. Here's the 10 kilohertz signal. I can adjust it. That must be clipping right there. So I can't go any higher. Let's see. 5, 10, 15, 20, 25. Yep, that's probably clipping. So we'll turn that back a little bit. And let's turn this up. That way I can get a larger waveform on the screen. And a little bit of wiggling going on up here. Not much down there. Let me try something else. Let me put the scope right at the output. I'm running through all these clip leads and things. Oh yeah, that's even better. Wow, that is a beautiful waveform. 10 kilohertz waveform on the LM1875 loaded with a 4 ohm load. Now of course at higher time divisions here on the scope, or I guess smaller time divisions, it's not going to be as fast because, well, audio amplifiers are not going to be nearly as fast. Plus, this amplifier has a low pass filter on the input to block RF, which any amplifier, audio amplifier, probably should have that. But anyway, this amp is very, very nice looking waveform. Yeah, it doesn't look as nice. You see, this is caused by the wiring, because when I hooked it direct to the output terminals, it wasn't doing that. But now I want to hook some capacitors across the output and see what this amplifier does. I want to see how it responds. Okay, ready to go here. I had to put a piece of aluminum under the load resistors because otherwise it would burn the bench, top of the bench here. So I have my arsenal of capacitors. These are film capacitors. I have a 1 nano, 10 nano, 100 nano, and 1000 nano. And we'll try each across the output here, see what happens. So this is called the step response of the amplifier. We want to see how the amplifier recovers when having the load, the pure capacitive load across its output, which amplifiers don't like. And the 1 nano does nothing. I'm not seeing any sort of effect. Now let me adjust this scope a little better here. I'm going to turn this on this way. Turn this up a little bit. You can see it a little better. It's like I'm putting nothing on it. So that's good. Okay, let's grab the 103. That'd be a 10 nano. Doesn't do a thing. That's what you call stable. Okay, next is the 104.1. Ah, there you see something starting. If I can get a connection there. Getting a little overshoot, but it corrects it without any ringing. For some reason, nothing on top though. I would expect some overshoot, but yeah, there's overshoot, but the amplifier corrects it right flat again. And the ultimate test is a 1 microfarad or 1000 nano. How would the amplifier deal with that? There we go. That is what you call a very extreme case, putting that kind of load on the amplifier. If I can get that to stay on there. There we go. So it overshoots, corrects, rings a little bit, but it brings it back into spec. So it's taking care of it. Like I say, that is a extreme case of putting that much load directly across the output of the amplifier. Let me stop that before it gets too hot. We are running quite a bit of power. The LM1875 always impressed me. It's just a good sounding chip. I mean, it's not a powerful chip. It's your 20-25 watt amplifier. But it sounds good. It's stable, especially if it's properly laid out on the board, you know, get the circuit grounds and everything right. Does a good job. Amplifiers do not like to drive capacitive loads, purely capacitive loads. It causes them to overshoot and try to correct. Normally an audio amplifier doesn't see a pure capacitance, like I say. There might be a small amount in the speaker leads, but there is some series resistance with that. But generally speaking, if the amplifier can handle 100 nanos, then it's doing a pretty good job. Apologize for the fan noise in the background. When I shoot these videos, I have to turn the furnace off, and it's pretty cold out today. And it makes a lot of noise, so I have to keep it off. So I'm running the 4000 watt heater, and that makes a lot of noise. But like I said before, this ringing, that's because of how we're hooked up with the leads here. Let me go directly across the output. Everything's nice and toasty now from running. Yep, that looks perfect. I want to check one more thing here. I'm going to crank this up to clipping. You can see odd things happen around clipping because that's the point where negative feedback can't control the amplifier during the clipping. So as it gets right, see right there's clipping. Right before that, on the bottom rail, you can see a little bit of wigulation, as I call it, technical term. But it does correct itself out and go back flat. Let me put a capacitor across. And it doesn't really do much. It might stretch it out a little bit, but it doesn't break out into oscillation or anything. And sometimes you see oscillation around clipping point of amplifiers. So I think we're in good shape there. So to me, this circuit is doing its job. It's nice and stable. No problems that I can see. Let's move on to another amplifier. Next amplifier to test is the TDA 7297. It is a Class AB type amp, and it's designed to run with 8 ohm load, so I switched out the 4 ohm load, put an 8 ohm. Doesn't have enough current, you know, the heatsink's not that big, and like I say, the current is not high enough capability to handle that. So yeah, it's not looking that nice, is it? It's not oscillating or anything, but we're getting some ringing going on. Let me adjust this. Okay, that's clipping right there. So turn that down so we can observe this. Okay, let's see what 1 nanofarad does. I'm not seeing any effect. Go up to 10. No effect. At least it's not causing it to break out into wild oscillation or anything. Here is a 100 nano. It does increase this overshoot. As you see me put it on, take it off, put it on. But it's not causing it to oscillate anymore. So it is a stable amplifier. It's not performing nearly as well as the 1875. Whoa, that broke it. Putting the 1 microfarad on there made it go a little crazy. Let's turn that back. Yeah, it can't handle that. Yeah, let me see what's going on here. I gotta hit this, and we'll turn this down a little bit. Yep. 1 microfarad across its output. It does not like that at all. Here is 100 nano again, no effect. So you can see how the amplifier finally did kind of go wonky on us there when we put the 1 microfarad capacitor on it. So now I'm going to try a Class D board. I want to see how that reacts. The thing with Class D boards are most of them have output filters already. So putting a capacitor across the output, I wouldn't expect it to have any effect other than reduce its frequency response, because you're shifting the pull frequency of its output filter. And with more capacitance, you're going to shift that down. But anyway, let's try it out and see what happens. Well, I had to break to feed the cat because he's jumping up on the bench and meowing in my face. So I got him fed and taken care of. So I have the TDA 3116 board. It's the board that I liked a lot. It was pretty good in the tests. But we'll look at the step response tests. So let me get it going here, and we'll point it to the scope. Okay, so here is the response. That's not looking too nice, is it? So this is cranked all the way up. So why are we seeing this with the 10 kilohertz square wave? Well, you have to remember these amps have filters which get rid of the switch mode noise, and they tune those things just outside of the audio band. It does make for an ugly looking step response. Let me put a capacitor across it. I'll just use 100 nano. The smaller ones are not going to make a difference with that kind of waveform. And this one doesn't do anything. Kind of what I expected. So now I'll go to the 1 microfarad. Look at that. Actually brings it up a little. It must be peaking the resonance of that filter. I think that's what's happening there. Snickers, what do you want? I just fed you. Now he's in here crying at me. So yeah, that's kind of interesting. Don't knock my camera over. We got a kitty on the bench. Kitty on the bench. Kitty on the bench. Wants to go up there and look outside. Okay, that's pretty nasty. Let me try an 8 ohm load and see what happens. Okay, so now I switch to a 8 ohm load, and that tells me that the output filter, which is an LC circuit, you know, an inductor and a capacitor, that circuit was designed to be used with 8 ohm loads. And that's one problem with Class D amplifiers. You know, they have the output filter, and that filter has to be tuned with the load impedance that you're going to run on the amplifier, which makes them kind of load dependent. So putting that 4 ohm load really drops the frequency, and it's probably starting to cut into its frequency response. And this response tells me it should handle 20 kilohertz just fine. You know, the 4 ohm load might as well. I'd have to test it. I have to go back and look at my test. But up, cat's coming down. Got to hold on to the camera. Rubbing his face on the camera lens. Move along, kitty. Step on the circuit. Yep, there you go. Alright. He's heading off to his chair, guaranteed. Take his afternoon nap. Where was I before I was so rudely interrupted? Yeah, so what I was saying, the values that are chosen for the output filter to remove the switch mode frequencies, just give the audio signal, you know, that's tuned for the load that you're going to use it with. I was seeing too much loss of frequency response with the 4 ohm load. And just for kicks, I'll put the capacitor across the output again. Well, that peaks it up. That causes the supply current to really jump. Not sure the amplifier would like that much. Let's try the 100 nano. And that peaks it up a little bit. Increases the current draw slightly from 1.09 amps to 1.1 amp doing that. The other capacitor jacked it up almost to 1.6 amps. So it's affecting that current. Again, interesting response. Last but not least, I'll show you a circuit with a big problem. Hey, quiet down over there. So this is an LM1875 board I made a long time ago. And I don't use it because I've tested it before and I know it has a problem already. So I have the 4 ohm load hooked up. And we're running 30 volts plus minus 15, just like in the first example, if I didn't mention it before. Apply power to the microcontroller. Yeah, this is pretty bad. It's oscillating. There are no capacitors hooked across the output and it's still oscillating. This has its problems. Let's see what happens if I add a capacitor. Will it get better or get worse? Oh, I got nothing there. Let's try, that was a 1 nano. Let's try a 10. Let's try 100. 10 made it slightly grow. Let's try the 1 microfarad. That actually cleaned it up a little bit. It made it oscillate down here. Snickers! Would you go somewhere, please? Kind of like the discrete amplifier test I did. So what is wrong with this amplifier? Well, it's all about supply bypassing. I don't have enough power supply bypass on it. So what I'm going to do is put some better supply bypassing on it and see what it does. See if it cleans it up any. So putting the on the positive rail there, you can see that cleaned it up some. Still not great. It needs more supply bypassing. That's on the negative rail. It still cleaned it up, putting that across the negative rail. So this is why you need plenty of supply bypassing, and might even try ceramic capacitors. And I really should have the electrolytic, the larger values, at least 100 microfarad across it as well. And it should clean up and look just as good as the one that's on the really well laid out board. So there you have it, taking a look at amplifier stability and step response. Another fun video. Hope you liked it. I'm sure Snickers did. And while I'm thinking of it, big thumbs up. I've hit 25,000 subscribers. Took long enough, but I finally got there. And let's focus this. Right, Snickers? Hey! Yeah, I'm talking to you. People want to see the Snickers. Well, that'll wrap it up. Catch you later.